Okay, so now we're going to talk about Log-Kummer correspondences. So in this video, I need a little bit of information about what happens when you go around one log-linked copy, and I guess I'll say this again. So, so one like little loop of the Log-Kummer correspondence. So, I know that's kind of self-referential, but you'll see what I mean. So we're going to take K over QP to be a finite extension, and then we're going to take a bunch of fields. These are going to be isomorphic to K as GK modules. And then what we're going to define, so this is the first indeterminacy diagram that we're going to do. And we're going to denote it by the symbol LK. And it's going to omit all, you can think of all as all the monoids being the identity. And there are going to be, so what we're going to do is we're going to have a bunch of log links between all of the fields, and the maps here are going to be the Kummer maps, the Machizuki-Kummer maps here between this and the core. So in the Annabelian version, again, let me also say this is IUT3 definition 1.1. Here I'm writing it out with fields, but okay, so this is what we'll have. So this is what we'll call the Log-Kummer indeterminacy diagram. Okay, and okay, these things will be interpreted by fields and monoids, or sorry, groups in monoids. And these will be interpreted, the core will be just interpreted within a single fundamental group. All right. And so the picture is it kind of looks like, looks like a diagram, looks like kind of like a correspondence. So we have this thing. So this is our Kummer map. So this goes from this thing that's interpreted in a more complicated structure to a thing that's interpreted in a less complicated structure. And these are described, the Kummer maps are a little bit as said about them in another video. Okay, and so this keeps going, and this keeps going. Okay, so this is what it looks like, and this is the core here. And from a previous video, we noted that if going around, let's do this. Let's get rid of that. So in the previous video, we noted that going around this loop like this, so going around a loop. So this was log pre here. So that, let me just write it out again. Cum 0 inverse composed with log pre, composed with cum 1. So this has the effect of giving log, acting as a log on the bottom here. And it doesn't matter which loop you do. Okay, so any of those loops will be the same. Another thing that we could say is that here, equivalently, we could say that here, if we go from here to here, right, that this map, by going, so Kummer of I to Kummer of J, so this will be log post. Okay, and so J is less than I, so this is I minus J times. So what it does is it does this other map where these are all isomorphisms, and it iterates that a number of times. So we have these two formulas here that come from just the way these maps are defined. I mean, it's almost, they're cooked up for this to happen. Okay. So this is our first Log-Kummer correspondence. Okay. All right, so now we're going to kind of soup these up. The two souped up versions are the following. So let's take so eventually we want to define indeterminacies on p-adic fields. All right. So the first version. So fix fields K1 through Km. So these are p-adic, all finite extensions of QP. We're going to let A be in Km. Okay, so it doesn't really matter which one it is, but for since Machizuki uses the last one, we'll use the last one. And we consider the following indeterminacy diagram. So here we're going to have monoids acting on these sets. So we're going to have it like this. So we're going to have here a to the n. So this is just a monoid generated by n. I guess we're going to include 0 into our thing. So n is equal to 1 up to m of k. Oh, let's say u. We're using u's here. Ku bar. So this is a product of fields. Okay, and then we're going to continue like this here. And we'll do the product of u is equal to 1 up to m Ku bar. Okay, and then we're going to have, okay, and so I guess we should start with 0 here, a minus 1 here, and then we're going to continue this. U is equal to 1 up to m Ku1, and this continues like so. And so this is going to be the map f minus 1. This is going to be the map f0, I guess. And then these are the maps. We're going to have these maps here: G0, G0, G1, G minus 1. It keeps going into the core version, an. We're going to have the product here. U is equal to 1 up to m of Kuc. Okay, so these are all going to be copies. So these are all copies of the fields. So Kui is going to be isomorphic to Ku. So for u is 1 up to m. And then we're going to index them like so. Okay, and then now I need to define what these things are. So so the maps fi. So these are going to be alpha I, beta I. So these need to be maps of monoid sets, right? Where here alpha I. So this is equal to the identity, and it just goes from a to the n to a to the n. And beta I, right, this is going to be equal to beta I. So this is equal to the log. So it's going to be the product of the pre-logs here. Log of Ku. Okay, and then we could take the logarithm, the ith logarithm here. From u is equal to 1 up to m. So here, again, this is going to be, we're using the notation Ku log I, like so. Okay, and so the 0th one is just the 0th one. And so this thing, when I write the product down below, I really mean we're going to take these logarithms here, log I, component-wise. So these log pre Ku log I. Okay, so Km. So sorry, this is Km. This is K1. K1 to Km. We take the product of all those. Okay, and so then now we need to define the actions. So the actions here, an cross this product, u is equal to oh no. Okay, so I was running out of room anyway. So so here we have the maps of monoid sets, like so. And then we have the action, and the action only acts on the last component here. And so I have in my notes that this is actually coordinate independent. So here, see how we had to like translate back to the 0th node, act, and then go back. So I'm told that this is coordinate independent by myself. I believe it is, but I would actually check this again before taking my word for it. But I think the point is that you can do this action without specifying which node. But okay, so this is the Log-Kummer correspondence for a tuple, which we've used this notation to make it. So eventually we're going to want to get an action on tensor products. Okay, so note that for given a so now we'll make our first definition. So for omega, a subset of K1 cross Km, so identified with the core. So and A in Km. So what we'll define is we define we define omega of Ind3 of A to be equal. This is going to be defined to be equal to omega of the indeterminacies of that diagram LKM of A. Okay, so this is our first. So this is the product version of Ind3. Okay, so that's what we have here. Second, what we'll do is we're gonna start to pick up the definitions now of what this sort of indeterminacy is, and what we'll do is here's the next definition. So definition. So for omega, a subset of this free group on the product of these fields. So and A in Km again. So what do we do is we define omega tilde of Ind3. So omega tilde, we're starting with omega tilde. Ind3 of A. So this is going to be defined to be equal to, okay, omega of Ind3 of the free. Okay, so that's why we were worried about defining this functor, free LK MA here. So okay, so now this is nice because so this is the free version of Ind3. Okay, and so now we have a quick way of defining indeterminacies now because of all that work we did. Okay, and now we can get the final definition for Ind3. Okay, so what is the definition of Ind3? So so let's do some notation. So we'll let quote from the free group here on this field be this map here. Okay, so the tensor products over QP, which takes a tuple. Okay, so this is so I underline things. So this is the free group of a set. I underline it to denote that it's the element of the free group. And we map this to x1 tensor xm. And so we extend this definition linearly. Okay, so this is this quotient. And this is surjective. Okay, and so so now the definition of Ind3. So for omega, a subset of the tensor product of fields, and A in Km, so we define, so omega of Ind3 of A to be equal to, okay, so we define it to be equal to the quotient of the, what we do is we take the inverse image in the free group. We take the indeterminacy there. And then we take the quotient back. Okay, so this is Ind3 of a subset of a tensor product space. All right, that's great. All right, so now we did all that work, the kind of like tedious definitions, but to just define this indeterminacy and what it means. Okay, this isn't defined in the papers. He just states this, and I think maybe considers this to be obvious. Okay, and so what we'll do is we take this, and then we'll prove an upper bound for this thing. Okay, so let me just remark that, so finally let me make a remark here, is that this A, an element of Km, is baked into the definition of the indeterminacy diagram. Okay, and for this reason, we define, okay, so for this reason we define A dot omega of Ind3. So this is defined to be equal to omega Ind3 of A. Okay, so this is what we mean by this. Okay, and so one of the questions we can have, so now we can start to have questions. Is it true? So in practice, this will be the tape parameter, and it'll be acting on some things. So so in practice, one question we can have is it the case that A dot omega of Ind3, right, is defined to be equal to A dot omega of Ind3? Okay, so this is so do these things commute, right? All right, and no. So all right, and so now I'm going to talk about computations involving this and estimates involving these things. Thank you.